And here's the solution for worksheet 2. Here is an equation for a spring. This is the force equals the spring constant times x, or delta x, the same thing. So spring constant is 1,000 newtons per meter. It says make the maximum displacement 0.25 meters, so that would be right there, 0.25 meters. And that means the largest force is going to be 250 newtons according to the equation. So there's the graph that describes that spring's behavior. It says graphically determine the amount of energy. I'll talk about that in a second. If you just use our equation for elastic potential energy, 1/2 kx squared, you get 5 joules when it's stretched to 10 centimeters. And it turns out on a force versus stretch graph that the area under the graph is equal to the energy. And here in yellow, that is shown. And here's the calculation, calculating the area of the yellow triangle you see to the left using just the base to 0.1 meters and the height to 100 newtons. It also comes out to 5 joules. And likewise down below, to get the energy in the spring when it's stretched from 15 to 25 centimeters, or 0.15 to 0.25 meters, you have to figure out the energy at 0.15 meters and then at 0.25 meters and take the difference, and that's 20 joules. And on the graph, it's the area of that green trapezoid, which we see calculated here, and it comes out as well to 20 joules. Questions 3 through 5 use this force versus stretch graph shown here to the left. And the spring constants for each are just found by getting the slopes. You can pick any 2 points. Since it starts from 0, it makes sense to use the 0 stretch point. And then any 2 convenient points that lie on the grid. And here's the calculation for the steeper spring constant, and this one for the less steep graph, which is a lower spring constant. The amount of force required to stretch the spring 3 meters. Just reading the graph, you're at 3 meters, and we have 15 newtons for the lower steepness line and 24 newtons for the line that's steeper. And those are the forces required on the spring to stretch it 3 meters. Elastic potential energy when stretched 3 meters, just using our equation for elastic potential energy for spring 1 and for spring 2. And finally, determine the amount that spring 2 needs to be stretched in order to store 24 joules of energy, using our energy for elastic potential energy and solving for x and plugging in the values that we know. We get 3.1 meters, which is just a little more than the 3 meters we calculated for here when we see that it was 22.5 joules, and this was for 24 joules. So it makes sense. It's just a little more than 3 meters. Question 6, we have a spring that has this spring constant, and it's pulled that distance, stretched that distance, and held motionless. So here is a force diagram for that situation. All forces are balanced, and using Hooke's law for an ideal spring, we calculate a 3 Newton tension force would be acting on the spring at that point. Next problem, spring constant is 20 newtons per meter for this spring right here. The coefficient of static friction, meaning the friction where it's not moving, so the spring would be stretched, pulling on the block, but the block wouldn't be moving because of static friction. The force diagram would look like this in that case. And then at what point would it start to slide back is when the tension force will be equal to the friction force and then get greater. So that means we have to figure out the stretch at which we hit that friction, that static friction level. Static friction using the front equation is 4 newtons. That means anything over 4 newtons of force will cause the object to move and overcome the static friction and start to move. And so we use Hooke's law to figure out the stretch when we know the force is equal to 4 newtons. And it would be the force of 4 newtons divided by the spring constant. 4 newtons divided by 20 is 1/5 or 0.2 meters is the distance to stretch the spring, so that the spring would be pulling with 4 newtons of force and would overcome the friction and start to move. And the last problem here is just a pie chart sequence that shows elastic potential energy becoming kinetic energy, back to elastic to kinetic, while the dissipated energy increases the whole time.